Welcome to today's paper reading. Today's paper is titled, A Comprehensive Survey of Compression Algorithms for Language Models. This paper was published on the AR14 preprint by Seungcheol Park and colleagues from Seoul National University. The introduction of this paper highlights the pressing need for compressing language models to address issues such as increased carbon emissions and high maintenance costs due to their large size. Various compression algorithms have been proposed, including pruning, quantization, knowledge distillation, low-rank approximation, parameter sharing, and efficient neural architecture design. This paper conducts an extensive survey focusing on low-cost compression algorithms applicable to large language models, comparing their performance, and summarizing the overall trend of their development. Table 1 provides a comprehensive list of symbols and their descriptions used throughout the paper, which are essential for understanding the language model compression techniques discussed. The table includes symbols for pre-trained language models, PLM, compressed language models, S, and various functions such as the multi-head attention, MHA, function. These symbols are crucial for interpreting the mathematical formulations and algorithms presented in the study. The pre-trained language model, PLM, compression problem is defined as generating a small yet accurate model S from a large PLM T and dataset D, while meeting specific cost constraints such as flops, memory usage, and latency. The transformer architecture, which is widely used in NLP, consists of multiple layers with MHA and FN sublayers, and includes layer normalization. Various compression algorithms are employed to reduce the cost of PLMs, including pruning, quantization, and knowledge distillation, as well as low-rank approximation and parameter sharing. Efficient architecture design is also crucial for reducing the computational and memory costs associated with PLMs. Figure 1 illustrates the two main variants of the transformer architecture used in language models. The first variant, encoder-only transformers, are designed for natural language understanding tasks such as sentence similarity and question answering. These models utilize bidirectional self-attention to generate embeddings that reflect contextual information within an input sequence. The second variant, decoder-only transformers, are tailored for natural language generation tasks like question answering and code generation. These models employ unidirectional masked self-attention, which only attends to current and previous tokens, allowing for autoregressive prediction of output tokens. Figure 2 provides a detailed illustration of the three core mechanisms within the transformer architecture: multi-head attention, MHA, feed-forward network, FN, and layer normalization. MHA is crucial for capturing contextual information between tokens through a self-attention mechanism. FFN, on the other hand, focuses on refining the information within individual tokens using a position-wise feed-forward network. Lastly, layer normalization ensures that each token embedding is normalized, which helps in stabilizing and accelerating the training process. Figure 3 illustrates the mechanism of the straight-through estimator, ST. ST is a technique used to pass upstream gradients directly to the next node during backpropagation, which is particularly useful for models involving non-differentiable functions like the round function, RF. In the forward pass, weights are quantized using RF, and the loss is computed. During the backward pass, the gradient of the weight matrix with respect to the loss is approximated via ST, allowing for gradient updates. This process is essential for quantization-aware training, QAT, enabling the training of models with quantized weights. Figure 4 illustrates the process of pruning a neural network with two layers, demonstrating both unstructured and structured pruning methods. Unstructured pruning, as shown in B, involves the removal of individual weights, resulting in a sparse weight matrix that requires special representation formats for efficient storage and computation. In contrast, structured pruning, depicted in C, involves the removal of entire neurons, leading to a dense weight matrix that is more efficient to store and compute. The figure highlights the trade-off between model accuracy and efficiency, with larger pruning granularities generally leading to more efficient, but potentially less accurate models. The pruning process aims to reduce the size of the model and improve its efficiency, making it more suitable for deployment on resource-constrained devices. Pruning algorithms are designed to identify and remove unnecessary components within pre-trained language models, PLMs, to create more compact and efficient models. These algorithms can significantly speed up inference on commodity hardware, as demonstrated by examples like ZipLM, which accelerates BERT inference by up to 15 times with minimal accuracy loss. Pruning can be done at various granularities, from individual weights and unstructured pruning to larger units like neurons and attention heads and structured pruning. This choice involves a trade-off between model efficiency and accuracy. Pruning strategies can be categorized into high-cost and low-cost methods. High-cost strategies involve extensive retraining on large datasets to ensure high accuracy, while low-cost strategies focus on efficient mask search and error compensation using smaller calibration datasets, reducing the overall computational cost. Figure 5 illustrates the different pruning granularities concerning weights, A, and tokens, B. The dotted square boxes represent each pruning granularity, and the weights for the embedding dimension are colored in pink for simplicity. The dimension of token embeddings in attention heads is denoted as. Table 3 provides a comparison of various pruning algorithms specifically designed for decoder-only transformers, evaluated on the Wikitext2 datasets. The table highlights different pruning granularities such as weights, W, 2:4 sparsity, neurons, N, attention heads, H, and sublayers, S. It also reports the compression rates achieved by these algorithms, ranging from 48.5% to 70.0%. Additionally, the perplexity scores of the pruned models are presented, with lower values indicating better performance. The table further includes information on the speedups achieved by certain algorithms, providing insights into the efficiency gains post-pruning. Figure 6 compares high-cost and low-cost pruning algorithms, focusing on the size of datasets and running times. High-cost pruning algorithms generate an accurate compressed model through a computation-intensive retraining process on a large training dataset, which can take up to 40 hours. In contrast, low-cost pruning algorithms address the issue by substituting an expensive retraining process with a lightweight calibration process on a small calibration dataset, which takes only about 10 minutes. Both methods aim to generate an accurate prune model, but they differ significantly in the resources required for the pruning process. Quantization is a technique that reduces the bit width of model parameters to compress large-scale models while maintaining their accuracy. This section introduces various quantization schemes, categorized by uniformity of quantization steps and levels, as well as by the cost of the quantization process. High-cost methods involve retraining or fine-tuning, while low-cost methods do not. The OPTQ algorithm is highlighted as a representative method for large language model compression, capable of quantizing models to under 3 bits with minimal performance loss. Improvements to OPTQ, such as OWQ and RPTQ, address specific challenges like preserving activation outliers and optimizing inference speed. Table 4 provides a detailed comparison of various quantization algorithms applied to encoder-only transformers, specifically on the MNLI QQP and Squad 1.1 benchmarks. The table categorizes the methods based on the uniformity of quantization, uniform or non-uniform, and the cost associated with the quantization process, high or low. It highlights the compression rates achieved by each method, the differences in accuracy or F1 score compared to the uncompressed model, and the speed-up factors observed. This comparison is crucial for understanding the trade-offs between model size reduction and maintaining performance across different quantization techniques. Figure 7 compares 8-bit affine and scale quantization methods. Affine quantization involves a non-zero integer offset, z, which allows for precise representation of original values but introduces computational overhead. In contrast, scale quantization employs a symmetric clipping range, avoiding this overhead by using symmetric quantized values. This figure highlights the differences in calibration symmetry and computational efficiency between the two quantization schemes. Table 5 provides a detailed comparison of various quantization algorithms specifically designed for decoder-only transformers, evaluated on the Wikitext2 dataset. The table highlights the perplexity scores, which are indicative of the model's performance, with lower values representing better results. It categorizes the algorithms based on their quantization uniformity and computational costs, distinguishing between uniform and non-uniform quantization methods. Additionally, it contrasts high-cost algorithms that require retraining or fine-tuning against low-cost algorithms that do not, emphasizing the trade-offs between performance and computational efficiency. This comparison is crucial for understanding the effectiveness and practicality of different quantization strategies in large language models. Figure 8 illustrates various quantization schemes including A. Naive round to nearest, RTN, uniform quantization, B. Non-uniform quantization using low-bit floating point, C. Non-uniform quantization using log-scaled values, D. Binary-coded non-uniform quantization, and E. Codebook-based non-uniform quantization. Each scheme offers a different approach to quantizing neural network models, aiming to balance computational efficiency and model accuracy. Figure 9 illustrates the differences between high-cost and low-cost quantization strategies. High-cost quantization involves retraining or fine-tuning the model after quantization to recover from accuracy degradation, as shown in Part A. This process requires access to the training or fine-tuning dataset. In contrast, low-cost quantization, depicted in Part B, employs post-training quantization, PTQ, which quantizes the pre-trained model without further training. This method only necessitates a small subset of training data for calibration, making it faster and less resource-intensive. The figure highlights that while high-cost methods aim to preserve accuracy through retraining, low-cost methods prioritize speed and efficiency by avoiding the retraining process. Figure 10 illustrates the process of quantizing FP16 weights and token embeddings into INT4 values using OPTQ and its variants. The figure shows how OWQ and RPTQ manage outliers to preserve accuracy, with dashed elements in and representing outlier-related weights. The superscript indicates reordering of matrices or vectors. The quantizers N represent OPTQ and round to nearest, RTN, respectively, used in the quantization process. This section introduces various compression methods for large language models, LLMs, including knowledge distillation, KD, low-rank approximation, LRA, and parameter sharing. KD transfers knowledge from a large teacher model to a smaller student model, improving the student's accuracy. LRA reduces model size by decomposing high-dimensional matrices into lower-dimensional ones. Parameter sharing compresses models by reusing weights across different parts of the model. Efficient architecture design enhances model efficiency through manual design or neural architecture search, NAS. NAS aims to find the most efficient architecture from a pool of possible designs. This section also details the low-rank adaptation, LoRa, algorithm, which fine-tunes models by updating low-rank adapters, significantly reducing memory footprint during fine-tuning. LoRa's compatibility with other compression and parameter-efficient fine-tuning, PFT, algorithms enhances its effectiveness. Table 6 presents a comparison of the performance of various knowledge distillation, KD, algorithms applied to encoder-only transformers on the MNLI, QQP, and Squad 1.1 benchmarks. The table summarizes the experimental results of KD algorithms that distill knowledge from a pre-trained BERT-based model to a compressed model with fewer sublayers. A 50% compression rate indicates that the student model contains half the number of sublayers of the teacher model. The table details the distillation sources used, the layer matching strategies employed, the compression rate, and the resulting accuracy/F1 score differences and speedup on the specified benchmarks. Table 7 presents a detailed comparison of various low-rank approximation algorithms applied to encoder-only transformers, focusing on their impact on the accuracy of pre-trained language models, PLMs, across three key benchmarks, MNLI, QQP, and Squad 1.1. The table highlights the effectiveness of different algorithms in achieving significant compression rates, with some methods reaching up to 97.91% compression without substantial loss in accuracy. Key algorithms evaluated include singular value decomposition, SVD, Fisher-weighted SVD, FWSVD, low-rank adaptation, LoRa, and adaptive low-rank adaptation, ADA-LoRa. These methods are crucial for reducing the memory footprint and computational requirements of large language models while maintaining their performance. In this discussion, we explore various types of compression algorithms for language models. Pruning algorithms offer significant acceleration, up to 15 times faster inference on GPUs. Quantization algorithms show high compression rates, with a maximum acceleration of 3.9 times faster inference. Knowledge distillation algorithms improve the accuracy of compressed models. For successful compression, it is crucial to incorporate a task-specific objective function and use an iterative, cost-efficient process to preserve useful features. Promising research areas include developing low-cost iterative algorithms, directly optimizing the objective function, and integrating parameter-efficient fine-tuning, PFT, with high-cost algorithms. In this paper, the authors have conducted a comprehensive survey of language model compression algorithms. These include techniques such as pruning, quantization, and knowledge distillation. The study also covers compression methods for both encoder-only and decoder-only transformer models, highlighting efficient architecture design. The authors have detailed background knowledge and 3 representative algorithms to enhance readers' understanding. They discuss the value of each compression algorithm type and outline 2 desired properties for successful low-cost compression algorithms. Finally, the paper introduces promising research topics focusing on cost-effective compression algorithms for large language models, LLMs, which are considered the most important language models in the field. Thank you for watching.